All right, maybe let's get started. So welcome to this Bootstrap payroll section. So there'll be going to be 4 talks, and the first talk will be 25 minutes, followed by some questions, and then there'll be 3 more talks, 15 minutes each, and again some 5 minutes for questions. And please, before asking questions, please wait for the microphone so we can record your questions. And our first speaker is Balt van Rees, and he's going to talk about constraining Glueball couplings. Please.
Right. Thanks a lot. Many thanks to the organizers for putting together what has so far been a really nice conference. I'm sure it's going to be great also from now on. So in the next 25 minutes, I'd like to talk a bit about a paper I wrote with that has this archive number with Andrea and Aditya about Glueball couplings, and a bit more generally, of course, I'd like to talk about the S-matrix bootstrap and the numerical implementation of S-matrix bootstrap, I guess. So first, what are Glueballs? Why are we interested in what are these Glueball couplings? How am I going to define them, and why are we interested in Glueballs? So Glueballs, in my dictionary, are the stable particles that you see in pure Young-Mills theories, at least, at very long distances. So this is Young-Mills theory, no quarks, just pure glue. This is, for example, we can take 4-dimensional Young-Mills theory, say SU3, obviously an interesting theory. And then what do we know about the stable particles, or what do we know more generally about Glueballs? Well, if you ask ChatGPT to draw you a Glueball, it comes up with something like that. So that's not particularly useful. But if you ask, for example, some lattice experts, they have actual numbers. So here is the spectrum of masses. This is not mass squared, this is a mass. The spectrum of stable particles, and these are the quantum numbers, the spin and the parity and charge number. So we see that this is the list of stable particles, and they see on the lattice a bunch of other resonances. But these are all unstable because, for example, if you have a scalar of mass in units, right? These are units where the lightest Glueball has mass 1. If you see a scalar of mass 2, you know it's going to be unstable and decay into a 2 Glueball state. So it's a finite list of numbers, and this is a thing that the lattice is extremely good at extracting. You see we have some digits of precision, and you have to work a little bit to get these spins, but I wasn't going to talk about all the details. So for me, this is just an output from the lattice. So this is something we know. But you can, of course, ask a lot more about this theory. You can ask, what about scattering of these Glueballs, right? I can set up an initial state with 2, say the lightest scalar Glueball, which was the guy with mass 1, and I scatter them, and out comes a bunch of other Glueballs. So what would be the Glueball S-matrix? Can we say something about that? Well, we can, of course, this is just, in the end, it's just some complicated function. But we can ask some more qualitative features. Does this have Regge trajectories? Does it obey, say, the Fosser bound? Does it maybe saturate it? What kind of dispersion relations does it obey? And what are potentially the couplings that enter in this S-matrix? And this is extremely difficult on the lattice. People can extract some stuff from the lattice, and that is one of the reasons we're actually looking at this, because hopefully there will be predictions in 1 or 2 years from the lattice about some aspects of this S-matrix. But a lot of these things are basically completely out of reach. So then the question is, can we as people from the Bootstrap community say something from first principles about this S-matrix? And so that's the question we tried to partially answer in the paper. Okay, first principles. So where do we start? Well, we can start, if we really want to start at first principles, I think we should start. There's a bit of a echo, but okay. The other microphone is, you got it, I think so.
I think there's one.
Okay, I'll just stand here. Maybe it's better. So where do we start? We can start from the Weidmann axioms, because generally it is, I mean, people can have all kinds of issues with them, but let me say that I believe that Young-Mills theory and the continuum limit obeys the Weidmann axioms. Then you have to postulate one more thing to get interesting stuff that I need, which is that there exists one particle state that is isolated. So it's isolated from the vacuum, it is a finite non-zero mass, and also everything else has an even higher mass with a finite gap. And if you make those assumptions, then there's a beautiful theory called Hague-Ruel theory that I learned about way too late in my career. So to fix that, we are going to put out, hopefully in a month or so, a nice review of this theory. That says that if you assume this, the S matrix exists in a mathematically rigorous sense. So what they show is that there exist these multi-particle states that you all learn about in standard quantum field theory, the in states and the out states, standard quantum field theory course. And of course, then there exists an overlap between these states, and that is your S matrix. So that's really nice. So we have an S matrix in Young-Mills theory, according to my axioms. What does this S matrix obey? Well, actually, the postulate of unitarity of an S matrix is kind of the unitarity of the S matrix is kind of a postulate in the sense that you have to postulate some kind of completeness where you say that, well, if I scatter two of these Glueballs with each other, then what comes out is always describable by anything in the out states, any of the multi-particle states. So that's a reasonable thing, because with probability 1 at the LHC, the finite state is a bunch of particles. So that's a postulate in the axiomatic field theory approach, and that leads to unitarity. And then you have to have some stupid technical assumption, which is the Weidmann axioms say that the Weidmann correlators exist, but that doesn't mean that time-ordered correlators automatically exist. So if you give me that small extension of the Weidmann axioms, then you can derive the LSZ prescriptions. And from the LSZ prescriptions, there's a huge amount of work to derive things like analyticity and crossing symmetry. This is also something that that was done in the 1960s, the community has largely forgotten. So to fix that, we'll hopefully put out in the next year part 2 of our review, which is going to discuss how you go from this to that. But then so we know that scattering amplitudes have some domain of analyticity and obey some form of crossing symmetry. So let me see what I can do with these 3 things and say something about Glueball scattering. So of course, because to make my life easier, I'm going to look, as everybody does, at the 2-to-2 scattering elastic process of the lightest scalar Glueball in the theory, the guy with mass 1. So this is the process schematically. We all know, right? This is the 2-to-2 amplitude, disconnected stuff, momentum conserving delta function, and then the scattering amplitude T of S and T. And of course, S, T, and U are the Mandelstam invariants. They sum to 4, so U is not independent from the others. And in physical processes, S needs to be greater than 4. Remember, my mass is 1, so it's 4m squared normally, but m is 1. And T and U should both be negative, so in the ST plane, S greater than 4, T negative, and U should also be negative, so 4 minus S minus T should be negative. So this green region is physical 1, 2, 3, 4 scattering. Another thing I'm going to need is that this scattering amplitude obeys some partial wave decomposition, which converges in a region that's strictly bigger than this green region. Where here you see the Legendre function, the Legendre polynomials as a function of the scattering angle, that's 1 plus 2t over s minus 4. And then these fj of s are the physical input. So what I'm going to do later is I'm going to parameterize the scattering amplitude almost entirely by this fj of s. So I'm just going to say the scattering amplitude for me is equivalent to giving the fj of s, and I will say for s greater than 4. And then there's a little bit of extra information, but that's roughly the part of the amplitude I'm going to, how I'm going to describe the amplitude. So I said analyticity, crossing, and unitarity, so let me go over what that means. First, I want to talk a little bit about the analytic structure, and then in the next slide I'll give you some constraints from analyticity. And here we see crossing and unitarity coming up, so this is 2 slides down. But for now, let's talk a little bit about the analytic structure first. So the scattering amplitude for this lightest Glueball is known to be, from this chain of arguments that I gave you before, essentially from the Weidmann axioms, is known to be analytic in the complex S-plane for some interval of t. There's some lower bound minus something that I always get wrong, and it doesn't matter for us, so I didn't want to write it on the slide. So this is correct, but it's not given. Except for the expected singularities, which is that the branch cut starts at 4, and then for every bound state, there's a pole. So we had, for every bound state that can appear. So two identical scalars cannot give you a vector, so from the previous, and it also cannot give you parity odd stuff or whatever. So from the finite list that I gave you before, there are actually 4 states that can give a pole. One is the guy itself at the mass 1, and then there's a spin 2 guy, another spin 0 guy, and another spin 2 guy. So this is not to scale, this 1.99 squared in particular is very, very close to 4. So it's actually a bit debatable whether this guy is stable or not, but I just put it there for now. And near the pole, this is what the thing looked like. So in the complex S-plane, it has a pole at, say, mu squared. The residue is minus g squared, and this g is very important. We're going to look at this g. And then the residue is some polynomial in t, the other variable, of degree L, where L is the spin, so spin 2 or 0. And then here at 4, you get the branch cut. So this is what it looks like in the complex S-plane for this interval, plus... so there are these singularities, but also the images on the crossing. So, for example, if I have a pole at s equals 1, then I also have another pole at 4 minus t. 4 minus 1 minus t, which is 3 minus t. The thing we try to answer is to see what is the maximal allowed value from first principles of these coupling constants g. That's what I'm interested in. So these coupling constants g, there are 1, 2, 3, 4 of them, and we're going to try to see what the maximal possible value is of these coupling constants.
Was this 3 level or was this?
This is non-perturbative. This is literally this. It's this analyticity. So it's completely non-perturbative. It's a positive number by something called extended unitarity. In 3 level, it would be, of course, a 3-point coupling squared. In this business, I guess there is no other independent definition of the 3-point coupling, at least not something I can think of rigorously. So it's not necessarily, it's a positive number, so I'm always free to write it as g squared. Yeah, thanks.
Sorry, can I ask a question?
Yes,
Yeah.
I'm also.
It happens that this excitation with mass squared equal 4 is unstable. So what happens to the branch cut? The branch cut will be washed away, and then.
No, if this guy is unstable, the branch cut is always there because there are always the 2 particle states besides the single particle states. So the lattice people, you see, I think they see them as a bunch of discrete stuff because they are in finite volume.
So just the tip of the branch cut just shifts. Right?
No, the tip starts always at 4 because the lattice people don't see it because the lattice people, right, they work in finite volume, but the tip should always be in the continuum limit. It's always exactly at 4. And then this one is either stable and then it is a pole below 4, or it is unstable and then this 1.99 would not be correct. It would be 2.01. So then it would be here. And then actually it should also have a small unit imaginary parts. So then it becomes a pole, the second sheet.
And then the spectrum, you just take it as an input from the...
Yeah, I'm going to take it as an input.
So
Yeah.
you cannot build it.
I cannot, no. And also, I cannot predict these couplings, right? I mean, we're just going to see what the maximal possible value is. Now, what else am I going to do? So this was a discussion of analyticity to tell you what these couplings are, because we're going to bound them, so I have to tell you what they are. So this is the definition of the couplings. It's the residue of this pole. And then... let me go back. There's analyticity, crossing, and unitarity. So I have to tell you a little bit more what I do with analyticity. And that's this horrible slide with the Roy equations. So you can, from analyticity, you write down a dispersion relation. You use crossing symmetry. You use the partial wave decomposition, all of that partial wave decomposition I introduced. And then you get some complicated sets of equations, which are called the Roy equations. And they hold for some interval of s that had to do with this finite interval of t for the analyticity picture that I gave you, and for all even spins. And this is the equation. And it says that the real part of the partial wave is given, roughly speaking, up to some junk that I'll come to, it's roughly speaking by the imaginary part of the partial wave. So it's like a dispersion relation. But because you use crossing symmetry, you see here a sum over all spins L with some kernel that has an Lj in it, and this is the spin j partial wave. So it's complicated, and then there is also a contribution from each of the poles. So we had 4 of them with some coupling constant g squared. And then there is one subtraction constant, which is basically the amplitude at some crossing symmetric point. So this is a subtraction constant in this first relation. So it's a few lines of derivation. And then there's a lot of kinematical junk that I just wrote to show you that it is kinematical junk. Right? S naught equals 2, T naught equals 2. With that, I can define this K. With that, I can define this R as K multiplied by Legendre polynomials. And then I can this R with the superscript J as R integrated against some other Legendre polynomials. So really here, there's no physics. Right? All the physics, if you know the chi, the g's, and the f's, then you can write down the right-hand side and the left-hand side better match this. Otherwise, you don't have analyticity. So it's not, I'm using not all the analyticity, I'm just using a little bit of analyticity to get to these equations. But the f's are going to be my important degrees of freedom. So this is what the f's should obey. So here are the Roy equations again. I wrote them a little bit smaller so they fit on one line. So I said this equals 0. Then there's a few more constraints that these degrees of freedom have to obey. One is from another crossing equation, which says that this is true with some R with some superscript n. I'm not going to tell you what it is, but this should be true for all odd n. And then there's unitarity, which says that for all physical energies and even spins, this should also be true. This matrix should be positive semi-definite.
What are the F's?
The F's were the partial waves. They're here. It's that decomposition. So, so this should be true by unitarity. You see the trace of this matrix is positive by construction, and the determinant being positive is the usual unitarity condition. So I write it as a positive semi-definite constraint. The thing I wanted to do is trace out the allowed the maximal values of the coupling. So let's take a linear combination of all the possible couplings squared. So Vp with some vector that I choose times Gp squared, summed over all the poles. And let's try to maximize this over the set of all Gp's, chi, the subtraction constants, and partial waves. What is this? Well, we recognize this as a semi-definite program. There are linear constraints. You see everything is linear in these variables. And except for one positive semi-definite matrix constraint. And the matrix entries are also linear in the variables. So this is a semi-definite program of infinite order, actually, because I have S as a continuous variable. I have a continuous infinity of constraints because of this. This should hold for all S and all even spins. And I also have a continuous set of degrees of freedom, the Fj of S. So I have to do something to make this numerically tractable, but essentially it's an infinite dimensional semi-definite program. So I am obviously going way too slow. So then there is a thing I have to talk about, which is duality. I'd like to discuss that briefly, and then I'll skip probably some discussion of the results. Where these were our, so let's write a Lagrange function, a Lagrangian that does the job for us, that implements these constraints. So roughly speaking, I write a Lagrange function with the thing I want to maximize, and then Lagrange multipliers for each of my constraints. So I have so-called dual variables, which are Lagrange multipliers. So this is an equality constraint. This is just the Roy equation, but written smaller still, so that it fits on with this on one line. And I multiplied with the Lagrange multiplier, and since it should hold for all S and all spin, so I have this Lagrange multiplier as a function of S and J. And this I have a continuous Lagrange multiplier for the continuous constraint. And then I have some Lagrange multipliers for the crossing and some Lagrange multiplier for the positive semi-definiteness. So this is a little bit schematic, but inequality constraints are roughly implemented by multiplying them with a matrix that obeys its own inequality constraints. So this Yj of S is some positive semi-definite matrix. So the thing we want to do next is go to the dual problem, where we now integrate out all the purple primal variables, which is fairly simple because everything is linear in the primal variables. And then we work with the dual variables. So this idea of passing to the dual was basically done first here, although they didn't talk about duality. And Andrea and Amit revisited that and extended it quite a bit and introduced this notion of duality here in 2021. So we want to pass to the dual. What happens? Why do we want to pass to the dual? And let me take a small detour and talk about this duality in semi-definite programming or linear programming in this one slide. So it's very simple. Suppose you have some Lagrange function, depends on a bunch of primal variables, and obeys some equality and inequality constraints. So we have a Lagrangian that looks like this. Some objective, some equality constraint, and some inequality constraint. So the problem that this Lagrange function captures is you maximize the objective such that the equality constraint holds and the inequality constraint holds with some direction. So NP is less than A. So one thing we could have done was to discretize this space, because in my mind this is an infinite dimensional space. This is complicated, so we had to truncate. We can truncate it and discretize it. Then we still have to make sure that it obeys all the constraints. And if we arrive at some discretization that somehow we can show solves all the constraints, then of course we get an estimate. We don't get a rigorous bound, because we're just looking around in the space of all possible p's that obeys the constraint, but in a subspace, because we discretize the problem. So that would be the primal problem, and you get valid estimates, but you never get a bound. But you get a bound in the following way. You look at the dual problem, which you get by integrating out p, and well, this dual variable had to be positive. If you integrate out p, you get one constraint, which is this one, that is 0 from the integration out of p, and you get an objective which is d dot a. And d dot a you're now supposed to minimize instead of maximize. And this thing, let me now truncate this to a finite dimensional problem. So I discretize d, and I still am somehow able to solve the infinity of constraints. Then I claim I get a bound on whatever this c dot p could be in my original problem. And independently of the discretization, this bound is completely rigorous. It's solid. And the proof is very simple, because let me look at c dot p for any p that obeys these constraints. Well, this d obeys this constraint, so I can replace the c with whatever is here. So I do that, I replace the c by the dual constraints. Then there's part of it is 0, and then the inequality constraint I can bound in this way, because there's this inequality and di is positive, so I don't get the sign flip. That was problematic when I derived the slide, but okay, I figured it out now. And di is positive, and then it's less than di dot a. So you can have a really crude approximation for this di. You get a crappy bound, but you get a rigorous bound. So you get rigorous bound by passing through the dual. That's what I wanted to say. So that's what we did. And in this slide, I say that we integrate out the primal variables exactly, so we formulate the dual problem. It still has infinitely many constraints, and we have to check that those are obeyed. Then we truncate the space of dual variables to something finite. Ideally, we wouldn't do it, but we have finite computational resources, so we truncate it to finite dimensional space. We still check that the infinity of constraints that we get can be obeyed. We do it, of course, still numerically, but we also check some analytic stuff at large spin and large s. And then we claim, up to this caveat that the constraints should really all be obeyed, we have some rigorous upper bounds on this combination. So that's what we did. I have 5 more minutes. 2 more? Okay. So these are the results. So for example, you can put in so now you know the game, and we can just do this. So we can take a single scalar bound state. We get some region like this, some no region. That is the new result. And here you see that we get multiple bounds because we have multiple discretizations. So if we have a more fine-grained discretization, we get a better bound. And I like this plot because this is a result. This green curve is a thing we obtained with an ansatz of the primal problem a long time ago, well, in 2017. And when we derived this curve, I was a little bit worried, because our primal ansatz looked a little bit weird, and I wasn't entirely sure if everything was completely rigorous. There were some questions there, but now we have a completely rigorous result, which more or less traces this curve. So that's nice. But this was a single scalar bound state of mass mb squared, and here you see mb squared, it varies between 0 and 4, and here you get the upper bound of the coupling. That's not Glueballs. This is a single spin 2 bound state. I'm going to skip this. So this is the Glueball results. Here we try to maximize each coupling individually. So we have 4 of these guys, right? G, H, G star, and H star. So I've now given them names. And these are the maximal values of the coupling. And we also did one result where we just dropped this guy from the list. We just killed this pole, and then we get some slightly lower values. So these are maximal values. They're big numbers, but they don't seem to be completely crazy. There's an old lattice result which is semi-crazy. It's not super rigorous, but they get 50 for this coupling, but not. So one thing we can say is that actually that's here, the 1, and we would kind of exclude the 50 if the 1 would be the only state. So this 50, if it would be true, then we would say, well, then at least you need more bound states in the theory. So that was kind of nice. And we also have a 3-dimensional plot where we just maximize in all kinds of directions. This is the allowed space of the 3 couplings, GG, G star, and GH. So here we included this guy, but we just left the H star, but we left its coefficient completely free. And there's some designated. So the maximum that you saw on the previous slide is obtained here, and another maximum is obtained there. So now we have bounds, and now it's up to the lattice. We were talking to the lattice people. We showed them this plot, and it's up to them to see whether their results, how they fit into this 3D shape. So this is my conclusion slide, and since I'm the first speaker and it is in my interest that everybody stays on time, let me skip that and conclude here. So thank you very much.
Any question?
Yeah.
So if the 1.99 goes at the threshold, I mean, firstly, do you know what the amplitude looks like?
No. Well, yeah, we can look at the extremal amplitude, but not because we use the partial waves as our primal variables. We actually know some of the partial waves only, and only for the ones that are. So we don't construct like in the primal method the full amplitudes. We actually only know these. And as it happens, only for a finite interval of S and for finitely many spins.
But you have access to what the amplitude looks like near the threshold, for instance, right?
Yeah, from above.
From above, yeah. So if the 1.99, does it have this 1/square root S minus 4? Or does it go to a constant?
It probably should, but we haven't checked. I don't know if we checked it in detail.
There's this thing that it can have either of 2 behaviors, but okay.
Yeah, it's like, so if you put a pole exactly at threshold, that would violate unitarity, right?
Yeah, but then okay.
So the coupling should go down like it does here with the square root, so that as you move this thing to 4, there should be square root behavior where the coupling goes to 0. This, of course, we know it for the scalar very well. For spin 2, here we see even something else entirely, so I'm not sure what this is. And the 1.99 should sort of obey qualitatively the same behavior, I think.
Other questions?
So, does your dual amplitude which saturates this boundary like also satisfy Froissart bound in the dual approach? Or?
It is what we get from the dual approach is very crude. Like I said, we only get some partial waves. Technically, we get, because they're the partial waves, as you integrate them out, they become Lagrange multipliers. So in principle, if you solve the problem, you know all the Lagrange multipliers, but it's like the partial waves are nice, and then they are 0, I think, after a certain energy. And I think the same is true for high spin, and so then you would obey the Froissart bound because your partial waves at high spin are just 0. So then it's fine. But it's really obviously not a full analytic amplitude, right? Because those things cannot be exactly 0. And that's because we forgot about part of the analyticity constraints. We just impose some.
Thank you.
Maybe last question.
Yeah, at some point you said, when you presented the dual, you said so it should be rigorous up to a caveat, which was
to solve, right? So what if I don't solve all the constraints, if I forget about some? That means that basically here some of the primal variables, I just forgot about them. So
when you integrated out everything,
if you integrate them all out, you get infinitely many constraints because you have infinitely many primal variables. So the only caveat is that, right, you have to solve the infinity of constraints rigorously. And of course, numerically, we don't really check, but this is common in the bootstrap, right? It's like we have a functional, and the functional needs to be positive for all spin and all delta, and numerically, we don't really check that. So.
But it's not like delta that you put 20% in the program. It's more like spin where you come.
Yeah, here we didn't. We also discretized the delta space. Yeah. And the equivalent of the delta space is the S space, and we discretized it instead of checking it continuously.
All right, that's thankful again.